Right. So, we are going to start on a new chapter which is going to discuss some generic classes of algorithms for distributed computing systems. So, the title of this chapter is wave and traversal algorithms. So, we are going to study two types of algorithms. One is called a wave algorithm, the other is called a traversal algorithm. Now, these are not specific to any particular application, these are generic classes of algorithms very popularly used in distributed computing. So, let us see what defines a wave algorithm. A wave algorithm is a distributed algorithm that satisfies the following three requirements. The first requirement is that each computation is finite. So, termination is a requirement of a wave algorithm. Each computation contains at least one decide event. So, decide event is a special type of event and each computation must contain at least one decide event. Okay. Depending on instances of wave algorithms, the criteria for reaching the decide event will vary, but the requirement is there should be a decide event. And the dependence is that in each computation each decide event is causally preceded by an event in each process. So, therefore, the algorithm must touch every process in the system and every process must respond to it by taking some action such that the decide event is causally preceded by an event in each process. All right. Let me give you an intuitive flavor of what a wave algorithm is about. So, a wave algorithm starts in a particular process, okay, and then the wave propagates to its neighbors, all right, and then the neighbors in turn propagate the messages, some kind of events to its neighbors, all right. So, this is how the wave propagates. So, it is like this, that this is one frontier of the wave and this is another frontier of the wave, and then again it propagates to other nodes, right, but there are not infinite number of nodes, right. So, at some point of time there will be no other nodes, new nodes to go to. So, the wave will start receding backwards, right. Now, how does a wave work? If you go to physics, you will see that the way that a wave works is like this, that there is a particle which has some energy. Okay. Now, when this is transmitted to the neighboring particles, each of these neighboring particles becomes a source of its own wave, right. So, it starts propagating that energy to all its neighbors, right, and some of that may come back here also, right. So, it is sending some, when this one gets the wave, it is going to send out its own wavelets, and some node here can receive multiple waves from multiple sides, right. That is how the wave propagates, right. And now, remember the last condition, that there has to be some decide event which typically happens in the initiator. This must be causally preceded by events at all other processes. So, that means that the wave must propagate to all other processes and then their effects are somehow coming back to the originator, and that is where the originator takes some decision, right, and then it terminates. Now, it may all sound very philosophical at this point of time, but we will see through practical examples that how wave algorithms can be used to propagate information in distributed systems, and there are we will see lots of different applications of these algorithms. The second class of okay, so let us take an example of a wave algorithm. So, this is a simple echo algorithm. The algorithm is going to send out a wave which will reach all the nodes, and then the wave is going to come back to the originator, and when the wave has subsided, that is there is no more waves, then the algorithm will terminate. Okay. This is typically used to broadcast some information in a distributed system, where the media is not point to point, does not give you point to point connection. So, you actually have to use intermediate nodes to propagate the information. So, in this algorithm we have a counter called RECP. This is the code for process P. Okay. So, the process P maintains an array, or rather a counter of the number of received messages, and it maintains the identity of its father. Okay. This father will get defined in the course of the algorithm. Okay. In other words, the father is the first process from which it receives the wave. Okay. Now, this is what the initiator of the algorithm does. So, this is only executed by the initiator. So, what the initiator does is, for all q which are neighbors of the process P, it sends a token to q. So, the initiator sends a token to all neighbors, all its neighbors, and then it expects to get the token back from each one of them. So, what does it do? It checks the value of the count rec p, while that is less than the number of neighbors that it has. It does the following thing: receive token and increment rec p. So, what is this loop doing? This loop is actually waiting to get back tokens from every neighbor. See, what we are only checking is that it gets back, if there are k neighbors, we are just checking that it gets back k tokens, right. We are just checking that it gets back k tokens, and then we are coming out of this. The decide event is in the initiator, and the initiator decides when it has got back k tokens, where k is the number of neighbors, right. That we will try to see whether that can happen or not. Right. Let us complete the algorithm. For non-initiators, this is what happens. For non-initiators, the process P receives token from neighbor q. So, this is the first token that it is receiving, this is the first token. Then it sets father P equal to q. Okay. So, and then because it has already got one token, so it sets RECP to RECP plus 1. Initially RECP is 0. Okay. So, it sets RECP to RECP plus 1. Then for all neighbors which are not the father, for all nodes except from the one which from which it has received the token, it sends token to q. Okay. And then waits to get back that k minus 1 number of tokens. Okay. So, if it has k minus 1 other neighbors, then it waits to get k minus 1 tokens, and then finally it sends token to its father. Is that clear? Okay. So, this is the algorithm. Now, tell me that how is this guaranteed to reach all processes? Neighbors sending it to neighbors, they sending it to their neighbors and so on. So, it propagates to all nodes. If there is connected, there it will reach, right. So, it will reach all reachable processes, right, and then the processes, after they have sent out tokens to all their neighbors and got back the tokens, it sends reply back to the parent, right, and in that way it continues until the initiator gets back all the tokens. When the initiator gets back all the tokens, the algorithm terminates, right. Now, there are a few things that we must understand here. So, node 1 sends out messages, tokens to node 2, and it sends out one to node 3, right, but before this one reaches node 3, node 2's token reaches node 3 and node 4, right. So, the father of this one is this, the father of this one becomes this, right. Now, before it has sent out the tokens, it gets this one. What is it going to do? It will simply add it to its count. So, when it got this token, its REC 3 was 1 because it got this token. When it gets this token, it will get revised to 2, right, and it will also send tokens to all its neighbors including 1, right. So, you can get tokens even before you send out your tokens, you can get multiple tokens if even before you send out tokens, right, but the first one that you receive defines your parent, and for every other token that you receive you just increment count, right. Now, the question comes that along an edge, can a process send more than one token? There the answer is no. Why is the answer no? Because by the definition of the algorithm, we are just sending process I. If I look at process I and process J, process I is sending a token to process J only once, and process J is sending a token to process I only once, but along every edge of the process network, along every edge a token will go from I to J and a token will go from J to I. Is that clear? This you have to understand very clearly, otherwise we will see lot of algorithms where this understanding has to be there, that regardless of the order in which the messages travel, a token will go from I to J and a token will go from J to I. It can happen in any order, but that is what will happen, right. Okay. And finally, when the initiator has got back all its tokens, then we know that, right. Now, if we just look at the parents of every node, then after the wave algorithm has terminated, what does the parent pointers actually define on the network? It defines a tree rooted at the initiator, right. So, that is one nice way of constructing a tree to find out a spanning tree in the graph. Now, you might wonder, can we actually tweak it around a little bit so that we get a minimum spanning tree, right. So, these things we can think of. Can we tweak it around a little bit so that we get a shortest path tree? Okay. Probably that is what Chandy Mishra's algorithm will be doing, right. So, that is we have to understand that rooted at the initiator we are getting a tree, and the tokens are returning along the tree when the nodes have no other neighbors to send tokens to, and they have already got back tokens from all their other neighbors. So, the tokens are going out in a lot of different ways. So, you can see that the way the tokens are going out, this is how, if I draw for every process the node which first sends token to the other process, then we are going to get some tree like this, right, some tree like this, all right. The parents pointers will point like this, okay. Now, there will be other tokens also going around between other neighbors. For example, if these two nodes are neighbors, then there can be another token going around like this. If these two are neighbors, then there can be a token going like this and also in the other direction. So, there will be lot of tokens moving around the fronts of this tree, right, but the completion will work backwards along this tree. So, only when all the other fronts have been covered, that this node will start returning its token, this will return its token, then this one will return its token, right. So, always for every process the last token send is to its parent, right. So, when therefore, when this one gets back its tokens, it knows that there is nothing else left in the network, right, no token lying around anywhere on the network. So, it can decide and terminate. Okay. Is the broad idea clear about how this algorithm works? Then we will see lot of variants of this in due course of time. Okay. Before we go to that, let us look at the other class of algorithms that we want to talk about. These are called traversal algorithms. Now, as the name suggests, that in a traversal algorithm, rather than spreading out a wave like we did for wave algorithms, we will do a depth first kind of movement. So, the wave algorithm was like a breadth first traversal, but breadth first in parallel, right. In the traversal algorithm, we will go depth first, we will go down one sequence of processes, come back, then try another sequence and so on. Let us see the algorithm. A traversal algorithm is an algorithm with the following three properties. In each computation, there is one initiator which starts the algorithm by sending out exactly one message. A process, upon receipt of a message, either sends out one message or decides. Okay. Now, see, computation, the initiator starts by sending out only one message, obviously to one of its neighbors, and then when a process receives the message, it either sends out one message or it decides. The algorithm terminates in the initiator, and when this happens, each process has sent a message at least once, right. So, again every process has to be touched, okay, and each process must have sent a message at least once. Okay. Now, let us see an example, it will become clearer as we look at examples of this algorithm. Sequential polling. In this algorithm, a node sequentially polls each other node, right. Instead of the echo algorithm where we sent out a wave, here we are going to sequentially poll, right. So, for the initiator, while again we keep a count for the number of tokens received, while this is less than the number of neighbors, do send token to one neighbor, okay, then receive the token back from that neighbor and then increment RECP, increment the counter. When you are done with all your neighbors, then you decide. Okay. What does a non-initiator do? The non-initiator receives the token from Q, sends the token to Q. Right. All right. So, this assumes that the initiator is adjacent to every other process. So, it sequentially polls each one of them and gets back the reply, right. We are going to look at another interesting traversal algorithm. We will start it in this class, but we will, I believe that the discussion will continue into the next class. This is the classical depth first search algorithm in the distributed setting. So, distributed depth first search. This is an example of a traversal algorithm. So, in the depth first search we need that visited list, right. So, we also have this used PQ, this array of booleans, okay, for each q belonging to the neighbor of P. Now, this is the data structure maintained by P. Okay. Every time in a distributed algorithm we only give the code for process P. So, I will set used P q to be true when I have sort of visited that neighbor q or something like that. Okay. So, that is how I am going to use this array to indicate that I have already used the neighbor q, and I will have the identity of the father, which again is going to get defined as the algorithm proceeds. The identity of the father will get defined. The initiator of the algorithm will do the following thing. It will set father P equal to P, because its father is itself, it is the root of the tree. It will choose a neighbor, set use PQ equal to true and send the token to Q. Okay. Now, see, only one message is sent, right, by the initiator. Now, when a process receives a token from Q, this is what it is going to do. It will first check, is my father undefined? If so, then this is the first token that I am receiving, and if this is the first token that I am receiving, then I will set father of P to Q0. What is Q0? The node from which I have received the token, right. So, I will set it to that node Q0 will become my father. Now, if for all q belonging to the set of neighbors of P, we find that already used PQ is true, then we decide. If we find that for all neighbors we have already exhausted used PQ, then we decide. Otherwise, if there is a q a process Q who is a neighbor of the process P such that Q is not the father of P and Q is not yet used, which means we have not yet visited Q, right. Then we do the following. What does this line check? It checks whether there is any other neighbor other than the father to which we have not yet sent the token, right. Now remember that Q0 may not be the father also. Q0 can be the father or may not be the father. Q0 will be the father if this is the first time that you are getting the token. If this is not the first time that you are getting the token, then Q0 is not your father, someone else is your father who has sent you the token, right. So, if father P is not equal to Q0 and not used PQ0, okay, then we will send the token to Q0. So, we will choose Q equal to Q0 and then somewhere down here we will send this token to Q. Now, understand this thing very carefully. If we get the token from a process Q0 which is not my father, but I have not yet used Q0, which means I did not send the token to Q0 and Q0 has sent the token to me. I did not send the token to Q0, Q0 has sent the token to me, right. Then I will send the token back to Q0. Okay. All right. Q0 is not my father. I did not send the token to Q0. I got the token back from Q0, and I find that I got the token from a node which is not my father. In that case, I will select that node to be visited next. So, I will send the token to that node. Otherwise, if Q0 is used already, then we choose some Q belonging to the set of neighbors except the father with not used PQ. Some other not unvisited neighbor I will select except the father, right, and then I will set used PQ equal to true and send token to Q, right. Now, all this is under the case that there is some neighbor other than the father which is not yet visited. Now, if there is no such neighbor, only the father is left which is not used, then this is the last step. We set use P father P to true and send token to father P and then end, because after sending the token back to the father I am done, right. Okay. Now, let us understand through an example how this algorithm is working, right. So, let me draw the process network first, who is adjacent to which. So, 1, this is the network, okay. 2, let us say that the node 1 is the initiator, right. So, what will node 1 do first? It will send a token to one of its neighbors, right. So, it will send the token to one of its neighbors So, suppose it has sent the token to 3, right. Then what will be the parent of 3? Parent of 3 will be 1. So, this is the parent, 3 will be 1. Now, 3 will do what? It will forward the token to somebody. Now, let us look at the used arrays. Okay, so, let us look at used 1. So, what is used 1? 3 is now 1, right, true, because it has already sent it along this, right. What is this going to do? It will choose one of its neighbors. So, let us say that it chooses 4, right. So, now used 3 4 is true, and 4 knows 3 to be its parent. Now, 4 will see that there is no other neighbor which is not used except the parent. So, it will send the token back to the parent, token will go here, right. Now, what will 3 do? 3 can forward it to some other node which is not yet visited. Okay. So, suppose it sends it to 5. Okay. Let me just make it a little bit more interesting by putting an edge between 3 and 6. Okay. So, it has sent it to 5, and so used 3 5 is set to true, right. And what is the value of REC? It has got token back from okay. So, it has got token, it has sent the token to this, it has sent the token to this. Now, what is 5 going to do? 5 will again choose one of its neighbor and forward the token. So, let us say it sends it to 6, right. So, now used 5 6 is true. Now, what will 6 do? It will see that it has only one node neighbor. So, it will send it here, send the token here, and it will send use, it will set used 3 use 6 3 to true. Now, look at what happens in 3. 3 has got the token from a node which is not its parent, right. Its parent is 1. So, it has got a node which is not its parent, and what about used 3 6? It is not true, right. So, it will choose this one to send the token back, right. Now, see, this is always going to happen when you reach a cycle. When the depth first traversal goes down and then reaches a cycle, right. There, when you get the token back along a cycle, you will see that it has come from not your parent and it is not yet visited, right. So, if this has come back and this is not visited, so we will send it back along this. So, token will go back here. This is the backtracking that happens in a depth first search. this is where the backtracking is initiated. You get the token from a neighbor to whom you have not sent the token, right, but you have been visited by the token along some other path. So, that means you are already visited. If you are already visited, then whoever visited you again will now have to backtrack. So, that is why this is being sent back. Okay. And now that this is being sent back, again what will 6 see? 6 will see that there is no other used neighbor. So, it will send the token back to its parent, right. What will 5 see? 5 will see that it has a neighbor which is not yet visited other than its parent. Who is the parent of 5? 3 is the parent of 5. So, other than its parent there is still another node which is not visited. Which one? 1. So, it will send the token to 1. Now, what will 1 see? 1 will see that it is the token has come from somebody to which it has not sent it, right. So, that is again a cycle. Which cycle? This cycle 1 to 3, 3 to 5, 5 to 1. So, backtrack. So, this token will be sent back, right. Now, 5 has already used up 6 and 1. So, it will send the token back to 3, and 3 has already used 5, it has already used 6, it has already used 4. So, it will send it to 2, 2 will send it to 1, 1 will again detect a cycle. Why? Because it has got the token from a non-parent and that one was not visited. So, it will send the token back. This one has no other neighbors, so it will send its token back. Now, for 3 there is no other neighbor except the parent to send the token. So, 3 will send the token back. Now, 1 gets the token back and it terminates, right. When you get the token back from the child to which you had sent the token, then you know that this is done, right. So, that is what the initiator does. If you look at the initiator, that it sends the token to Q, and then when finally it gets the token back from the child, that is where it terminates. Okay. All right. So, this is the classical distributed version of the depth first search algorithm, right. Is there any doubt about this algorithm? Are you clear about its working? This is a traversal algorithm, right. Now, let us compare the echo algorithm with this algorithm. Both algorithms want to visit every node. What is the order of messages that we have in this algorithm? (2e). Why? Because along every edge the token is once going in this direction, once in the other direction, right. Okay. 2e. What about the number of time units, the number of cycles? What is the largest? See, messages are being sent in parallel, right, sometimes. So, what is the number of 2e time units? Because in every cycle only one message is in transit, unlike in the echo where parallelly messages are being sent. Here messages are being sent sequentially. At every point of time only one message is in transit, right. So, we have 2e time units, the algorithm's time complexity will be 2e and the number of messages is also 2e, right. What about the echo algorithm? What is the number of messages? 2e. What is the time complexity? The diameter of the thing, right. isn't it? Right. So, why do we at all use traversal algorithms? Echo algorithm uses same number of messages and yet does it in a lot shorter time. Congestion is okay, you might say that, but if congestion is not a problem, if you have sufficiently high bandwidth channels, then why should we at all go for a traversal algorithm? So, this traversal algorithm we will improve it. As of now it does not seem to be attractive, right, as compared to the echo algorithm. So, we will improve it by showing that some simple tricks can reduce the number of messages and the number of time units that are taken in this algorithm. Okay. Number of messages, you see, there is not much hope of improving, right, because you have to traverse all edges in any depth first traversal. Each edge has to be visited, right. You cannot work without visiting every edge, but we can make things better by reducing the number of time units, right, from 2e time units to something much lesser than that, right. That is what we are going to study in the next class. We will see improvements of the traversal algorithm first, and then we will study other wave and traversal algorithms in due course of time. Okay. Thank you.